Bismillahirrahmanirrahim. Assalamu alaikum students. Last time we were discussing second of thermodynamics and we stated it, this law. We gave the statement of Calvin Planck, which is in terms of the efficiency of a heat engine. So I continue that topic. Heat engines and the second law of thermodynamics. So this topic is continued from previous lecture. So I repeat the last statement which we gave in the last lecture. Statement was, it is impossible for an engine working in a cycle to produce no other effect than that of extracting heat from a heat reservoir and performing an equivalent amount of work. And we said that this heat engine will do other effect, and that effect is it will reject some heat to the cold reservoir. We can state this statement alternatively. We can see that we cannot have a perfect means 100% efficient heat engine, right? We cannot have a perfect, that is 100% efficient heat engine. And you know 100% efficient means that efficiency of the heat engine is 1. So the efficiency of a heat engine cannot be 1. So this statement is one of the statements of second law of thermodynamics, and this statement is called Kelvin Planck's statement. Now we give another statement of second law, which is in terms of refrigerator. Now first I will draw a schematic of refrigerator. So we have hot reservoir at temperature TH. We have cold reservoir at temperature TC. Then what refrigerator does, this is my refrigerator. Refrigerator. What it does, it takes heat, that be QC, from the cold reservoir rejects heat to the hot reservoir. We denote that by QH, but we keep it in modulus. In each cycle, but we have to perform W amount of work on the refrigerator, which can be in terms of electricity. So what is QC? QC is heat absorbed by the refrigerator from the cold reservoir, right? QH modulus is heat rejected to the hot reservoir and we know these quantities are per cycle because refrigerator, like heat engine, is a cyclic device. It will have a working substance which is performing cyclic process, and in each cycle it takes QC amount of heat from cold to reservoir, which is sometimes called a sink, and it rejects QH amount of heat to the hot reservoir, and we have to give W amount of work. We have to work on the system. Now, since we know from first law, of thermodynamics, net heat put into the system is equal to change in internal energy plus the work done by the system. Now, since the process is cyclic here, du is 0. There is no change in internal energy, so dq is dw. Now my dq is net heat put into the system, and that is qc minus qh. My qc minus qh is net heat put into the refrigerator, because QC enters and QH leaves, so net heat put in the system is QC minus QH. And system is not doing work, but we are doing work on the system. So I must write QC minus QH, QC minus QH is equal to minus W, because negative work indicates, according to a sign convention, work is being done on the system, right? I have written net heat put in the system is equal to minus W. Let this be my first. Now, what we want that this work should be 0. That is the ideal situation. We want a refrigerator which takes heat from the cold reservoir and rejects that heat to the hot reservoir without any input, without any electricity, without any work. That's an ideal situation, but second law of thermodynamics says that is impossible. Your refrigerator will take heat from the cold reservoir and give that heat to the hot reservoir, but it will cost some work always. This is second statement of the second law of thermodynamics. It's called Clausius statement of second law of thermodynamics. What does it say? It says like this. It says it is impossible for a refrigerator working in a cycle, because our refrigerator is working in a cycle. Working in a cycle to produce no other effect than the transfer of heat from a colder body, that's cold reservoir, to a hotter body, that's hot reservoir. This is the Clausius statement in terms of refrigerator. So it will always do other effect. That other effect is it will absorb the work from the surroundings. We define here a quantity called coefficient of performance, which gives the measure of performance of a refrigerator. So for a refrigerator, we define coefficient of performance. We denote it by eta. Is defined as QC over W. This is its definition. QC is the amount of heat taken by the refrigerator per cycle from cold reservoir, and W is the amount of heat which is done on the refrigerator by the surroundings. So over time, coefficient of performance of refrigerators have increased. We have increased it by making better refrigerators. That means we have minimized this work, but we cannot make this W equal to 0. And if we do that, then we will have a perfect refrigerator, which is impossible. You can say alternatively, Clausius statement this way also. You can say coefficient of performance of a refrigerator working in a cycle cannot be infinite. This W can't be 0. Or you can say we cannot have a perfect refrigerator, right? Now these statements are equivalent. You need to remember all the statements of second law are equivalent. So the statements are equivalent. Why not bring that? I'm just pointing out. The statements are equivalent means that one implies other. They are alternative ways of stating the same thing. My next topic is reversible and irreversible processes. Reversible and irreversible processes. What are reversible and irreversible processes? Now consider a simple process. For example, this is my hot reservoir. Hot reservoir, and it's my cold reservoir. Now let me make this figure differently. So let this be my hot reservoir and this be my cold reservoir. So it is hot reservoir. You can say it is some hot body. It is cold reservoir. Now consider a simple process. Which process? Conduction of a certain amount of heat, Q from hot reservoir to cold reservoir. Now follow my argument. I am saying I have this hot reservoir, it will have to have some temperature, and I have cold reservoir that will have some temperature. Since it is cold, its temperature will be less than hot reservoir. Now I am saying consider a simple process. Which process? Conduction of a certain amount of heat Q from hot reservoir to cold reservoir. That means I bring these two reservoirs in thermal contact. What will happen? Heat will flow from hot reservoir to cold reservoir. So Q amount of heat goes from hot reservoir to cold reservoir. The question is, can I reverse this process? Can I reverse this process? Reversing process means I have to bring cold reservoir and hot reservoir back to their initial states. If I am able, or if I manage to do that, if I manage to take this heat Q from the cold reservoir back to the hot reservoir, then I will conclude that conduction of heat from a hot to cold body is a reversible process, right? But that is impossible. Why? Because if this heat cannot go by itself to the hot reservoir, then what you have to do, you have to run a refrigerator, because to take heat from a cold to hot body, we use a refrigerator. Now, if you take this heat back to hot reservoir using a refrigerator, right, then this will lose this Q amount of heat, and you will transfer that Q plus W to the hot reservoir. Now, you cannot take Q only to this. You cannot have a ideal refrigerator. You need to put some work. You will have here Q, but in addition to that, you have to put some work on the refrigerator. So if you take this Q heat back to this, you are bringing cold reservoir to its initial state, but hot reservoir is not in its initial state, because W amount of heat is extra. Right? Now then, next step is what? You have extra amount of energy in the form of W in the hot reservoir. Now what you want to take that heat from the hot reservoir and make it work. But if you do that, you have to run what? Heat engine. And you cannot take this amount of heat and reject, do that amount of work, convert that amount of heat to work, and give that work to the surroundings, because some amount of heat will be rejected. So if you take this heat back to work, some heat will go into the cold reservoir. So if in trying to bring the hot reservoir to its initial state, you will make a change in cold reservoir. In trying to bring cold reservoir to its initial state, you will make a permanent change in hot reservoir. The cycle will keep on going. That means you can never bring the cold reservoir and hot reservoir, or I should say system and surroundings, back to their initial states. So this conduction of heat from a hot reservoir to a cold reservoir is an irreversible process. Irreversible process. Incidentally, I must tell you that we are in unit 2nd of our syllabus. We have completed first unit, we have entered 2nd unit. I repeat this argument, follow it. I am saying I have a cold reservoir, I have a hot reservoir. Now some heat Q goes from hot reservoir to cold reservoir. Now I want to check whether this process is reversible or not. If I bring the cold reservoir and hot reservoir back to their initial states, then this process is reversible. So for that, I have to take this Q heat, put it in hot reservoir. Now that can be done using refrigerator. Now all refrigerators, according to second law of thermodynamics, Clausius statement, I have to put Q amount of work. So if I take Q here, then in Q will be in hot reservoir, but an additional heat in the form of work will be available in the hot reservoir. Then if you want to take that back to the surroundings, that work, some heat will go into the cold reservoir because of the Kelvin-Planck statement. You cannot take heat from the cold reservoir, this hot reservoir, and convert that to work. Some amount of heat will go to the cold reservoir. This will keep on going. So this process is irreversible. There are many processes which are irreversible. This was the one explanation, one justification in order to make this clear to you what is irreversible process. So we define, now I give the definition. We define any process to be irreversible any process to be irreversible if the system and surroundings cannot be brought back to their initial states. So you can think of this cold and hot reservoir, one as system and second as surroundings. So we define any process to be irreversible if the system and surroundings cannot be brought back to their initial states. And you, as I have discussed, the conduction of heat from a hot reservoir to cold reservoir, this irreversibility is intimately connected with the second law of thermodynamics. Now we can find many irreversible processes in nature. Any process, you need to remember, any process that converts mechanical energy, into internal energy, is irreversible. I repeat, any process that converts mechanical energy into internal energy is irreversible. For example, if I have a table, all right, which has certain friction. Now I have a block on it. Now I push this block. It will travel certain distance and ultimately it will stop. What is actually happening? At the start, if it has mass m, it moves with speed v, then it has kinetic energy half mv square. As it moves along the table, due to friction, after some time, a bit time, first its speed decreases, its kinetic energy reduces, ultimately it stops and its kinetic energy becomes zero. Where does this kinetic energy or mechanical energy go? It actually increases the internal energy of the table and the block and the surrounding air. So in this process, mechanical energy gets converted into internal energy. So you cannot take internal energy of the block, table, internal back and make this block at the cost of that internal energy to move again. So this process is irreversible. You need to remember that The reversible process means what? Where you can bring the system and surroundings back to their initial states. You need to remember all real processes are irreversible. All real processes are irreversible, right? The reversible process is an idealization. All real processes on the earth are irreversible, right? So a reversible process is an idealization. We can approximate a process to be reversible. There are conditions for reversibility. What are the conditions? I list them. Conditions necessary for a process to be reversible. What are the conditions for a process to be reversible? First thing, no work must be done by friction, viscous forces, or other dissipative forces, those forces which waste energy, dissipative forces which produce heat. No work must be done by friction, viscous forces, or other dissipative forces which produce heat, because when work goes to heat, you cannot reverse it 100%. Second condition is there can be no heat conduction, due to a temperature difference. As we discussed, that if heat conducts due to temperature difference, hot to cold body, from hot to cold body, that is irreversible process. So there can be no heat conduction due to temperature difference. And third thing, the process must be quasi-static. Only then we can, the process must be, we can represent that on a PV diagram. The process must be quasi-static so that the system is always in an equilibrium state or infinitesimally near an equilibrium state. Near an equilibrium state. Remember the equilibrium state? We have already discussed it when we represent state of a system or gas in PV diagram. We said gas must be settled, right? Only then we can assign pressure volume to it and represent it on a PV diagram and represent quasi-static process in which, remember, in quasi-static process, piston moves with zero acceleration infinitely slowly. So all these three conditions must be satisfied by a process to be reversible. If any of the conditions is violated, process is irreversible. That means if this condition is violated, these two are not violated, process is irreversible. So you can see it is very difficult to eliminate all the friction, all viscous forces, dissipative forces, and to fulfill all these three conditions. So we can make a process reversible in practice only approximately. We cannot have perfect reversible process, but still we can approximate it to a large degree or extent, right? My next topic is the Carno engine. I will introduce it first. Now in 1824, a French engineer, Sadi Carnot, described an ideal reversible engine. Reversible engine means that the process, the working substance of this engine goes through the reversible process only, right? And it is ideal. That means you cannot have this engine in practice, right? It's an ideal reversible engine. It works in a simple cycle between two heat reservoirs, hot reservoir and cold reservoir. But important is Sadi Carnot described this ideal reversible engine and he found a theoretical limit on the efficiency of an engine in terms of the temperatures of the heat reservoirs. I repeat, Sadi Carnot described an ideal reversible engine working in a simple cycle between two heat reservoirs, and he found a theoretical limit. What is the maximum possible limit? That is the limit of efficiency of an engine in terms of the temperatures of the heat reservoirs, right? Now this ideal reversible engine described by Sadi Carnot is called Carnot's engine. Carno engine, right? We will describe its cycle. Before that, we will give the statement of Carnot theorem. What is the statement of Carnot theorem? Statement of because Carnot's results are given in this theorem or through this theorem called Carnot theorem. So statement of Carnot's theorem. Theorem states no engine working between two given heat reservoirs can be more efficient than a reversible engine working between those reservoirs. To understand the statement of this theorem, no engine working between two given heat reservoirs can be more efficient than a reversible engine working between those reservoirs. That means this statement says if we take two reservoirs and reservoirs are specified by their temperature. So if this is hot reservoir, it will have some temperature. You have cold reservoir, it will have some temperature. Now you operate between two given reservoirs, any engine, and find its efficiency. Now for all those heat engines which you operate between these two reservoirs, their efficiency will be always less than or equal to the efficiency of a reversible engine operating between these two reservoirs. And it will be equal in only one situation, when that other engine is also a reversible engine. Got it? I'm saying if I have a hot reservoir and cold reservoir, I specify them by their temperatures. I fix their temperatures when I'm saying given two reservoirs I have. I operate, for example, 1 million engines between them and find their efficiency. Let one of them be reversible engine. The efficiency of that reversible engine will be greater than all other heat engines operating between these two reservoirs. Right? Now we have a byproduct of this theorem, that is corollary. Corollary to Carnot's theorem. That is evident or obvious. Corollary is all reversible engines working between the same two reservoirs have the same efficiency. It follows from the Carnot theorem. You think about it, about how it follows at home. So I repeat the corollary. All reversible engines working between the same two reservoirs. Same two reservoirs means two reservoirs having a pair of temperatures. Same two reservoirs have the same efficiency. So if you operate 100, for example, 100 heat reservoirs between two given reservoirs, if all are reversible, they will have same efficiency. The Carnot's theorem is also expressed or stated in terms of refrigerators. Now stated, so Carnot's theorem in terms of refrigerators is simple. No refrigerator, this is theorem, no refrigerator working between two given heat reservoirs can have a greater coefficient of performance than a reversible refrigerator working between those reservoirs. No refrigerator working between two given heat reservoirs can have a greater coefficient of performance than a reversible refrigerator working between those reservoirs. So again, this statement is like the previous statement, but only in terms of refrigerators, instead of efficiency, we have coefficient of performance. And corollary will be all reversible refrigerators working between the same two reservoirs have the same coefficient of performance. So this is the corollary. All reversible refrigerators working between the same two reservoirs have the same coefficient of performance, right? Now I will continue with this topic. Next time, I will give you the homework. A simple question. An engine transfers 2000 joule of energy from a hot reservoir during a cycle and transfers and during a cycle and transfers 1500 joule as exhaust to a cold reservoir, right? Cold reservoir. Part E. Find the efficiency of the engine. Find the efficiency of the engine. This is part A. Part B is very simple. How much work does this engine do in one cycle? How much work does this engine do in one cycle? Repeat the question. An engine transfers 2000 joule of energy from a hot reservoir during a cycle and transfers 1500 joule of energy as exhaust to a cold reservoir. Find the efficiency of the engine. And part B is how much work does this engine do in one cycle? This is all for today. Do your homework. Thank you. God bless you. Assalamu alaikum.